The standard rule of geology is patience. Continents move at the speed fingernails grow. Canyons take millions of years to cut their channels. The Earth is old and it works slowly. That rule holds almost everywhere. And almost everywhere is the problem. In what is now northwestern Wyoming, 48.9 million years ago, 400 square miles of solid rock broke free from its foundation and crossed the landscape in minutes. Not years, not centuries, minutes. What it left behind broke one of the most fundamental laws in geology, and it took nearly 100 years of scientific argument to figure out how. The Wyoming of 48.9 million years ago bears no resemblance to the high desert basin it is today. The planet was deep in the Eocene climatic optimum, one of the warmest intervals in Earth's history. There were no permanent ice caps at either pole. Greenhouse gas concentrations were high, sea levels were elevated, and the region that would become Wyoming sat at a much lower elevation than it does now, receiving abundant rainfall into a humid subtropical basin. The landscape was dense, broadleaf forest. Paleobotanists reconstructing this environment from fossilized soils and preserved leaf impressions in the Bighorn Basin have identified palm ancestors, cycads, tree ferns, dawn redwoods, and sycamores. The ground beneath them was soft and wet, shallow rivers, expansive wetlands, mats of decaying vegetation. The animals that moved through this forest looked like rough prototypes of creatures that would come later. Eohippus, the earliest horse, was the size of a medium dog, with 4 toes on its front feet and 3 on the back, its padded feet suited to moving quietly through mud rather than galloping across open ground. Notharctus, a lemur-like primate, moved through the canopy on grasping hands, its forward-facing eyes tracking movement in the dense foliage. In the clearings, Brontotheres, massive rhinoceros-like herbivores distantly related to horses, browsed through the undergrowth. The apex predators included mesonychids, carnivorous ungulates with hooves and heavy bone-crushing jaws, and Diatryma, a flightless bird standing over 6 feet tall with a beak proportioned for killing. To the west, the Absaroka volcanic province was active. These were stratovolcanoes, the same architecture as Mount St. Helens or Mount Rainier, and they had been spewing thick ash and triggering lahars into the basin for a long time. Unlike the later Yellowstone supervolcano, which would eventually form through massive caldera-producing eruptions, the Absaroka chain was a series of individual towering peaks, each capable of sustained eruption, lahar generation, and localized ash fall across the basin. The animals in the forest had always lived under their shadow. On this particular day, the shadow was about to become something else entirely. The Absaroka volcanoes were forcing magma upward through the crust. That magma was moving into the vertical fracture lines running through the ancient limestone layers above. Limestone deposited when a shallow tropical sea covered this region roughly 350 million years ago during the Mississippian period. The magma intrusion acted as a hydraulic wedge, pressing against the base of a vast horizontal slab of that limestone and tilting it incrementally. Then came the earthquake. The static friction holding the slab in place broke. 400 square miles of solid rock began to move. The slab that detached was not a thin sheet. It ranged from 1 to 2 miles thick. Its total area covered roughly 400 square miles, comparable to the full landmass of the city of Los Angeles. This block of Madison limestone and dolomite, deposited over hundreds of millions of years, sheared off its foundation at the area near present-day Cook City, close to the Montana-Wyoming border, and began sliding southeast toward the Bighorn Basin. It moved at an estimated 50 to 100 miles per hour. That estimate comes from the physics of the system. The distance traveled, the driving force of the initial tectonic shove, and the near-zero friction conditions that sustained the movement. There is no direct instrument reading from 48.9 million years ago. But the geological evidence at the fault contact, the intact nature of the transported block, the absence of internal deformation consistent with slow creep, and the extreme thermal signatures recorded at the sliding boundary points only to catastrophically rapid transport. The first thing that would have registered, before anything was visible, was sound. The grinding of 2 miles of rock against its own foundation generates pressure that has no quiet release. The crack of limestone fracturing under compressive force travels faster than the rock itself. The leading edge of the slab bulldozed the subtropical forest at highway speed, and the air displaced ahead of it would have moved faster still, a pressure wave preceding the wall of stone. The forest went first. The rivers were dammed or rerouted instantly. The animals, the Brontotheres in the clearings, the Eohippus in the brush, the Notharctus in the canopy, had no warning that would have meant anything. The sky filled with rock dust and volcanic ash until daylight was gone. The slab traveled between 30 and 40 miles before it finally lost momentum and stopped. The lush, subtropical basin was gone. In its place, a barren, chaotic expanse of fractured limestone, billions of tons of displaced crust piled across a landscape that had been biologically crowded minutes before. The slab ran out of momentum and settled into its new position. The silence that followed was absolute. Over the following millennia, seeds colonized the fractured limestone surface. Soils began to form in the cracks. The ancestors of modern mammals slowly reclaimed the terrain. But the geology beneath them had been permanently rewritten, and it had left behind an anomaly that would not be properly noticed for another 48 million years. The first geologists to study the region in the early 20th century were looking at a landscape that erosion had been working on for nearly 50 million years. The vast majority of the original 400 square mile slab had long since broken down, weathered by rain, ice, and river systems, and carried off into basin sediment. Because the detachment had heavily fractured the limestone during transport, the rock was especially vulnerable to subsequent weathering. Shattered rock erodes faster than intact rock, and the Heart Mountain block had been shattered thoroughly by the trauma of the slide. What remained after 50 million years of that process were scattered remnants, isolated limestone peaks, sitting in geologically impossible positions across the Bighorn Basin. Heart Mountain, north of present-day Cody, Wyoming, is the largest of these survivors. The rock that makes up Heart Mountain is Madison limestone. It formed during the Mississippian period, approximately 350 million years ago, when a warm, shallow sea covered the region. Shells and skeletal material from marine organisms accumulated on that seafloor, compressing over time into dense carbonate rock. The rock directly beneath Heart Mountain is the Willwood Formation, a sedimentary unit deposited during the Eocene, roughly 50 million years ago, composed of the kind of river-deposited muds and silts consistent with the subtropical basin environment that existed at the time of the slide. The law of superposition is the foundational principle of stratigraphy. Older rock sits below younger rock because younger rock is deposited on top of what already exists. Heart Mountain inverts this completely. A 350 million-year-old peak sits on top of 50 million-year-old ground. The rock on top is 300 million years older than the rock it rests on. Early geologists identified this anomaly in the 1920s and 1940s. C.L. Dake and Walter Bucher recognized the stratigraphic impossibility and reached for the most available explanation: tectonic thrust. The prevailing model for moving mountains was compressional tectonics, the crust being squeezed together, forcing rock layers to override one another along thrust faults. A tectonic thrust would move old rock on top of younger ground. It fit the observation on the surface. It did not fit anything else. Thrust faults leave massive crumple zones at their leading edges, where the driven rock compresses against the material in its path. And Heart Mountain and its associated remnant peaks showed no crumpling. More critically, behind the mountain block, back toward the Cook City source area, there was a vast empty zone. Rock was simply missing, as if the crust had pulled away and left a gap. Tectonic compression squeezes material together. It does not pull it apart and leave a hole. The tectonic explanation was wrong. But the alternative, that the mountain had simply slid into position from somewhere else, created a problem that would take another 50 years to resolve. William Pierce of the United States Geological Survey spent the better part of 4 decades mapping the Heart Mountain area on horseback and on foot. His work, conducted from the 1950s through the 1980s, was meticulous and ultimately decisive. Pierce traced the detachment fault, the boundary surface along which the slab had slid, across the Bighorn Basin. He mapped the source zone near Cook City. He identified the clippy remnants, a geological term for isolated masses of rock that have been transported far from their original position and left stranded by subsequent erosion. He established the denuded zone, the empty area behind the block where rock was conspicuously absent, consistent with material that had departed rather than been compressed. He built the case piece by piece that Heart Mountain was not a tectonic feature but a gravity-driven detachment. The slab had broken off and slid downslope under its own weight. Pierce's work established the fact of the slide. It could not explain the mechanism. The physics problem is precise. For a solid object resting on a solid surface to slide under gravity, the gravitational force pulling it down the slope must exceed the frictional resistance holding it in place. The ratio between these forces is determined by the coefficient of friction, a measure of how much two surfaces resist sliding against each other. For limestone resting on other rock, the coefficient of friction is high. To move such a block under gravity alone, the slope beneath it typically needs to be at least 30 degrees. The detachment fault beneath Heart Mountain was mapped at a maximum of 2 degrees. In most places, it was functionally flat. 2 degrees is a slope so gradual that standing on it, a person would perceive it as level ground. The force required to push such a slab from behind only deepens the problem. If a tectonic or volcanic force tried to drive the block horizontally across a flat surface, overcoming that high coefficient of friction across a 400 square mile base, the compressive stress would shatter the rear of the limestone block before the block moved. The compressive strength of limestone cannot transmit enough force across that area to overcome friction at the base. Push the back of the slab, and the back of the slab breaks. Pierce hypothesized that fluid pressure from groundwater, amplified by seismic activity, might have temporarily lifted the rock off its foundation. The math was never fully satisfying for a slope that flat. He proved the slide was real. He could not close the physics. The paradox sat unresolved for decades. The geological record demanded the slide had happened, and the laws of friction said it was impossible. Understanding why the paradox was so resistant requires sitting with the numbers. A 400 square mile slab of rock, 2 miles thick at maximum, represents a mass that produces enormous downward pressure across its entire base. That pressure is what creates friction. The heavier the object, the more it presses into the surface beneath it, and the more friction opposes its movement. Weight is not an asset in sliding, it is the enemy. Place a heavy object on a flat wooden surface. It does not move. Tilt the surface slightly, and it still does not move. The friction holding it in place is proportional to how hard the object presses into the surface, and that is proportional to its weight. To make it slide on a nearly flat surface, something has to be placed between the object and the surface, a layer that breaks the direct contact and reduces friction to near zero. For the Heart Mountain slab, the question was what that layer could possibly be. The surface was rock, the object was rock. There was no visible medium between them that could have negated the friction of a 400 square mile contact zone. The answer was not found by looking at the mountain. It was found by looking at the dirt. In the late 1990s and into the early 2000s, structural geologists, including Edward Beutner and colleagues, among them David Malone and John Craddock, brought modern analytical tools to the exact boundary layer where the Heart Mountain slab had once contacted the stationary ground beneath it. They were not looking at the limestone peaks. They were examining the millimeter-scale fault contact, the precise geological interface where the slide had occurred. What they found there was pseudotachylite. Pseudotachylite is an extremely rare material. It is a glassy, dark rock that forms only under conditions of extreme frictional heat, typically in the deep rupture zones of major earthquakes or at the contact surfaces of meteorite impact craters. It is produced when friction generates enough heat to flash melt the rock at the contact surface. The temperatures required exceed 1,500 degrees Celsius. The rock does not gradually heat and soften. It melts in a fraction of a second. Veins of pseudotachylite running through the Heart Mountain fault contact meant that the rock at the base of the sliding slab had reached temperatures comparable to the surface of lava flows, instantaneously, under the pressure and friction of the moving mass. The contact rock had turned to glass, and glass, at those temperatures, is a lubricant. The paleomagnetic evidence confirmed the temperature reading independently. Rocks contain microscopic grains of magnetic minerals that align with the Earth's magnetic field at the time of formation and remain locked in that orientation as the rock cools. Subjecting rock to extreme heat resets those grains. They realign to the field present at the time of reheating. The magnetic grains at the Heart Mountain fault contact had been reset. They recorded a sudden and intense thermal event at the fault boundary, consistent with frictional flash melting. The glass was half the answer. The rock at the base of the Heart Mountain slab was composed primarily of limestone and dolomite, carbonate rocks, meaning they are built largely from calcium carbonate. When calcium carbonate is exposed to temperatures above roughly 1,500 degrees Celsius, a chemical reaction called carbonate dissociation occurs. The calcium carbonate breaks apart into calcium oxide, quicklime, and carbon dioxide gas. This reaction was happening across the entire base of the moving slab. Wherever frictional heat was being generated, CO2 was being produced in massive quantities along the fault contact. But the 2-mile thick slab was pressing down on top of it. The gas had nowhere to go. In the seconds following the initial break, ultra-high-pressure layer of superheated CO2 formed along the entire detachment surface. trapped between the moving slab above and the stationary ground below. The pressurized gas layer lifted the slab infinitesimally off its foundation. The direct rock-to-rock contact was broken. Friction dropped towards zero. 400 square miles of solid rock was riding on a cushion of its own decomposition products, molten glass and pressurized gas generated by the heat of its own movement. The slide had manufactured the only conditions under which it could continue. Movement produced heat, heat produced glass and gas eliminated friction, and eliminated friction allowed more movement. Each step fed the next. The system was self-sustaining from the moment it began. A fourth mechanism reinforced the cascade. The grinding of a 2-mile thick slab across its foundation produced immense vibrational energy, high-frequency waves propagating through the rock and debris at the fault contact. This acoustic fluidization caused the fragmented material at the base to temporarily lose its solid cohesion, behaving instead like a dense fluid. The same phenomenon allows massive avalanches to travel far beyond what simple friction calculations would predict. The vibration itself is part of the transport mechanism. The Heart Mountain Detachment was not a landslide in the conventional sense of a mass rolling and tumbling down a hill. It was a 400-square-mile geological hovercraft, a slab of continental crust levitated on flash-melted glass and exploding gas driven by the slight tilt the magma intrusion had created. Crossing the Wyoming basin at highway speed until the gas dissipated, the glass cooled, and the slab settled permanently into the Bighorn Basin floor. Pierce had been right about what happened. The modern geochemical analysis, the pseudotachylite, the paleomagnetic reset, the carbonate dissociation chemistry resolved what his field mapping alone could not. The event required both: the old-school geological detective work that established the fact of the slide, and the laboratory tools that found the mechanism in a layer of glass thinner than a thumbnail. Heart Mountain today is an isolated limestone peak north of Cody. It is a clippy, a surviving remnant of a slab that was once continuous across 400 square miles. The rest of that slab has been gone for tens of millions of years, eroded by rain and ice and river systems working on heavily fractured rock for 48.9 million years. What remains is large enough to be visible from the highway and geologically anomalous enough to have confused scientists for a century. Understanding how it got there is not an exercise in prehistoric geology alone. The mechanisms that drove the Heart Mountain Detachment, carbonate dissociation, frictional melt lubrication, acoustic fluidization, pressurized gas cushioning, are not unique to Eocene Wyoming. They operate wherever massive bodies of rock are subjected to sudden stress on low-angle surfaces. The most consequential modern setting for these same physics is not on land. It is at the flanks of oceanic volcanic islands. The Hawaiian Islands are built on thin oceanic crust. They are enormous, heavy structures, and their flanks, the sloping sides of the volcanic edifices, are geologically unstable. Geologists mapping the seafloor around Hawaii have identified the evidence of past flank collapses, massive submarine landslides that transported enormous volumes of rock across the flat ocean floor, far beyond what simple friction predictions allow. The Helena slump on the southern flank of Kilauea is a recognized unstable structure. The Canary Islands off the northwest coast of Africa present a similar profile. The flanks of these volcanic islands are steep and heavily loaded. Submarine landslide deposits from past collapses have been mapped across the Atlantic seafloor. In both environments, the same cascade applies. A volcanic earthquake or magma intrusion breaks the static friction holding the flank in place. The sliding rock generates frictional heat. Carbonate and silicate minerals in the contact zone decompose or melt. Gas and glass form at the fault boundary. The flank rides the cushion across the flat ocean floor. When a submarine flank collapse of sufficient volume occurs, the displacement of the water column above it generates a tsunami. The energy transfer from a rapidly moving mass of rock to the overlying ocean can produce waves that travel across entire ocean basins. But the scale of the wave depends on the volume of the collapse and its speed. And the hovercraft physics that allow high-speed travel on a flat surface are exactly the conditions that maximize both. The Heart Mountain Detachment is a frozen record of this process on land, where it can be walked across, sampled, and analyzed in ways that submarine collapses cannot be. The pseudotachylite veins in the Wyoming fault contact are the same material geologists look for in submarine core samples. The carbonate dissociation chemistry modeled from the Heart Mountain data is used to estimate the mobility of submarine volcanic collapses. The acoustic fluidization dynamics, first worked out here in the Bighorn Basin data, feed directly into numerical models of tsunami generation. Wyoming is, in this specific sense, a laboratory, one that has been sitting open for 48 million years, waiting for the right instruments. The Eocene jungle that was obliterated in those minutes 48.9 million years ago left almost no direct trace. The animals that were killed in the path of the slab were buried under billions of tons of limestone and long since returned to the carbon cycle. What survived was the mechanism, preserved in glass and gas chemistry in the fault contact, readable by anyone with the right instruments, and the patience Pierce demonstrated across 4 decades of fieldwork. The Earth does not always work slowly. Sometimes it works in minutes, at highway speed, across 400 square miles of subtropical forest. The lesson Heart Mountain preserves is that the threshold between stable and catastrophic is not always visible from the surface, and when that threshold breaks, the ground itself provides the conditions of its own destruction. The slide generated the heat generated the lubricant, and the lubricant allowed the slide to continue until Wyoming was permanently buried under stone. The system built its own escape from physics in real time. The rock under Wyoming turned into a hovercraft. The same physics are active today, sitting underneath the steep, heavily loaded flanks of oceanic volcanic islands scattered across the Pacific and the Atlantic, patient and entirely unannounced, waiting for a threshold that is not broken yet.